Okay, integrals using trig substitutions. Man, haven't we done this enough? Huh, tables. Could those tables be a clue? Or maybe we just didn't have any cows today. Okay, you probably remember we did an example like that and we got an answer like that. And then we said, okay, if we have the general form where we have an integral and inside the square root symbol is a squared minus x squared, every single time that's how it's going to come out looking. Of course, there were two other types of integrals. Instead of the x squared being subtracted, we could have x squared minus. And then, of course, there didn't necessarily have to be subtraction there. It could be addition. And, of course, with addition, the order does not matter. That's why there's only one of them with addition. Well, if we had done this time and time again, we would have discovered something, right? And again, the placement of the x, or whether or not there's a negative or positive, really changes the triangle I have to draw. When x squared is being subtracted, that told me that x was one of the legs, and then a plain old number was the hypotenuse, and we could use the sine function. But when it was x squared minus something, that's when the x had to be the hypotenuse. And since we didn't want the x to be in the denominator, we ended up using secant, so I could use hypotenuse over adjacent. And then the inevitable, when we have that addition in the middle, the x is going to be one of the legs, a plain old number will be one of the legs, and we're forced to use tangent. And those were the integrals that we've discovered, whoa, they are going to be a dead end with the skills we had at the time. So if we have an integral with a square root, and inside the square root is x squared minus a squared, notice we don't end up with anything like arc sine or arc secant or arc cosine or anything, right? We end up with natural log. But every single time, that's what the answer will look like. If we have an integral and there's a square root and it's x squared plus a squared, every single time, that's what the answer is going to look like. So the only one that's kind of the oddball was actually the one we could do step by step all the way through. Now, if you're thinking there's no way I'm going to memorize these, of course not. Right? We're functioning a little bit unusual, but in a school, and I don't care if you're talking about a high school, a community college, a university, a technical school, right? If you take a calculus class, you're going to have a textbook, and inside that textbook, whether it's actual physical paper textbook or an online textbook, there's a table of integrals, right? You're still expected to integrate a lot of things by hand, but they're like, hey, we're honest about this. There are some things you're just not going to be able to memorize, right? I expect you to become like very familiar with the unit circle. I expect you to memorize that sine squared theta plus cosine squared theta equals 1. There's no way you can memorize all these assorted bizarre integrals. And so there's always a table. Oh, that was the hint on that first screen. A table. There is a table of integrals. There are some of these that are just so wicked that say, you know what, if you see this general form, we're just going to let you know how it's going to play out. So let's try a couple of example questions here. Right? I see an integral. Now, if there had been an x outside that square root symbol, I could do a simple u substitution. But I don't have a plain old x outside. So I go to my integral table, And now, of course, an integral table would usually have, oh, I don't know, 50 different integrals, maybe 100 different integrals, depending on if you're looking at, introductory level calculus or, more advanced calculus. But there would be a big, long list on this table, and you try to find, well, what am I looking at? Well, of course, today you're only going to be looking at 3, right? There's only going to be 3 options. And you say, oh, I'm looking at one of these. I'm looking at an x squared minus a squared. Right? So when I look at that 144, I got to remember, okay, if that's a squared, that means it's 12 squared, right? So any place I see a squared, I'll just know, okay, I got 144. So what am I going to write down? Well, it looks like I got to put x over 2, so I better put my x over 2. I have to have a square root symbol. There's no choice there. I have to have my x squared. I have to have subtraction. Okay, now a squared, I mean, I could write it as 12 squared, but that'd be kind of silly. I'm going to actually write it as 144. Okay, I need a subtraction symbol. Now there's going to be a fraction, and the denominator has to be 2. Numerator, a squared, well, that's 144. Natural log, and inside the natural log is an absolute value symbol. If you remember with logarithms, we cannot take the logarithm of a negative number. That's why the absolute value symbol has to be there. In fact, we cannot even take a logarithm of 0, right? It has to be a positive value. Well, I have to put the x. I have to put a plus sign. I have to put a square root symbol. I have to put the x squared. I have to put a subtraction symbol. A squared, well, that's 144. Oh, I'm not done. There's a plus c. Notice I really don't get to make any choices, right? I don't sit there and go, gee, I need to understand what I'm doing, right? Because a lot of times in math, you really, really want to understand the process. And this is one of these situations where you're like, hey, it's a very complicated integral in calculus, but instead of trying to understand it, you look at the table and you use the equation that's in the table and you just plug in a couple of numbers, right? If you really can understand why this is the equation, you're way more advanced than a first-year calculus student, right? First-year calculus, even a second-year calculus student. I mean, come on, you're going to look at the table, you're going to try to pick the correct equation, and you're going to try to plug in the number. And I'm really not quite done with this one, because it looks like I can do one thing. I can reduce that silly fraction of 144 over 2, and I get 72. But otherwise, I'm done, right? I'm absolutely positively done. That's a little disturbing, a green guy with thumbs up. Oh, well. Now, is the whole assignment that easy? No, right? That table is going to help you with the integration, but guess what? If there are limits to the integration, we have to plug in numbers at the end. Same first step, though. I've got to go grab an integral table. And again, for this lesson, these are the only 3 choices we're going to look at, right? Because this is the famous trig substitution. And we're like, oh, which of these are we looking at? And I'm thinking, okay, I think I'm going to look at that third one, right? I got a square root of x squared plus a squared. So in this case, we got x squared plus 3 squared, right? 3 squared is 9. But I can just leave it as 9. Okay, so what do I have to write down? Notice I put a big set of parentheses because I know at the end I have to evaluate it at 4 and then evaluate it at 0. Okay, well, so what do I have to write down? Well, I have to have x over 2. I have to have a square root symbol. I have to have the x squared. I have to have the plus. Right? I'm not really doing any thinking here. I'm just copying what I see. A squared. Okay, well, that's going to be my 9. Then I need a plus sign. I have to have a fraction with a 2 on the bottom. A squared on top, well, that'll be my 9. I have to have a natural log, and inside the natural log, I have to have the absolute value symbol. I have to have an x. I have to have a plus sign. I have to have a square root symbol. I must put x squared. I must put a plus sign. Ooh, a squared. Okay, now I got to think a tiny bit. I got to put a 9. Now, instead of putting the plus c, I'm not going to have a constant because we have to evaluate this from 0 to 4. Right? Left to right, we would have started at 0 and we would have gone to 4. So, I've got to plug in the number 4. Triton! Triton! Well. Okay, apparently Triton's going to be quieter now. So what did we just do? I had to plug in the number 4, and we're going to figure out that answer. And then I plugged in the number 0. We got to figure out that answer. And then we'll take the answer from the 4, subtract the answer from the 0. Right, so when I saw an x, I had to plug in a 4. When I saw an x squared, well, 4 times 4 is 16. Then there's another place with an x, so I had to place a 4. Another place with an x squared, and 4 times 4 is 16. Then I had to substitute in the 0. So x over 2 became 0 over 2. X squared plus 9 became 0 plus 9. And x became a 0. And then x squared plus 9 became 0 plus 9. So how much can we tidy this up? Okay, I've got that 4 over 2. Well, 4 over 2, plain old 2. Inside the square root, I've got 16 plus 9, that's just 25. Inside a square root symbol, I see a 16 plus 9, that's 25. 0 over 2, of course, is just 0. Inside the square root symbol, 0 plus 9 is 9. Inside the square root symbol, 0 plus 9 is 9. Woo doggies. Okay, square root of 25 will become plain old 5. Square root of 25 will become plain old 5. Square root of 9, of course, will just be 3. Square root of 9 will be 3. Let's see here. 2 times 5, that's going to be 10. 4 plus 5, that's going to be 9. 0 times 3, 0. 0 plus 3 is 3. Okay, so we can pretty much throw that 0 in the recycle bin. So it looks like there's a 10 plus 9 halves natural log of 9. Subtract 9 halves natural log of 3. Now, of course, I don't need those absolute value symbols anymore because plain old 9 is a positive number, plain old 3 is a positive number. And since they both had a coefficient of 9 over 2, I can factor the coefficient out using the distributive property. Hey, we can condense the logarithms, right? They're both log base e, right? Natural log is log base e. And so if the bases match, we can condense. And of course, subtraction will condense with division. So it just becomes natural log of 9 over 3. And of course, 9 divided by 3 is 3. So if I want an exact answer, that's my exact answer. 10 plus 9 halves times the natural log of 3. Now, we could have a little bit of a debate, though, because some people say, hey, you know what? You can condense that logarithm further. Right? That coefficient of 9 halves could do that, right? We could declare that it's 10 plus natural log of 3 raised to the 9 halves power. But since we can't take the square root of 3 very nicely, most mathematicians would be like, no, just leave it as 10 plus 9 halves times the natural log of 3. Now, if I actually want an approximation, well, you know, natural log of 3 is going to be not too far from 1, right? I could use a calculator. And of course, the reason being is that, you know, the number e isn't that far from 3, right? E is about 2.7182818284599045, and then it starts going really weird after that. So e to the first power would be a little bit too small, right? Just about 2.7. E squared is kind of a bit too big, right? Because that's about 7.4. So I kind of knew that the natural log of 3 was going to be a little bit more than 1. And then, of course, I can, with a calculator, I can multiply that number by 9 halves, also known as 4.5. So, 4.5 times 1 is going to be a little bit more than 4.5. And actually, it's getting kind of close to 5. How about that? And then finally, you add 10. You say, okay. And then depending on the situation, maybe you round off to 1 decimal point, maybe you round off to 2 decimal points, maybe round off to 3, right? Depending on the situation or the directions asked. But now I've got a decimal approximation. So, of course, it's going to spell out worksheet, because I don't know what else it would possibly spell out. Although I must admit, the worksheet's kind of blocking a really beautiful scenic view. Oh, now it's fading away. And that's a nice conclusion for the PowerPoints.